Here's the first problem that I want to work on. I'm going to leave it small like this so I can write on the other side here. And let's look at the hold on a second. I've got a problem with my there we go. Here's the first problem I want to work on. And this actually is a very nice problem because it gives us an example of both how to start working with free body diagrams, but also the impact of looking at different systems when you do a calculation and how important it is to carefully define your system. So let me make this smaller and we'll start out. And the professor here is 65 kilograms. The cart is 12 kilograms and the equipment is 7 kilograms. And so the total mass of all of that, if you consider all of it, is 77 plus 7 or 84 kilograms. So that's the total mass. Now, with this second system, with the professor excluded, it's going to be just 12 plus 7 or 19 kilograms. So the mass of the second system in question is 19 kilograms and the mass for the first system in question is 84 kilograms. And then it says that she exerts a force of 150 newtons and the opposing force is 24 newtons. What is the acceleration? So to calculate the acceleration, we have to consider first the entire system, which includes her, because she is the one exerting the force. If we don't consider her, then we have no idea what the acceleration is. And the important thing to remember too is that the cart and her all accelerate at the same rate. So the free body diagram we're considering first is this free body diagram where the force of the floor on her and the cart leads to the acceleration. So F net is going to equal the force that she generates minus the resistant force, which is going to be 150 minus 24, or 126 newtons. And that is what results in the motion of all of this material here. And so if F is equal to ma, then A is going to equal F divided by m, which is going to be 126 divided by 84. So the acceleration here is 1.31 meters per second squared. So that's what the acceleration is. Now the second question is, what is this force exerted on the cart? Okay, now the force here is in the second system. Now this cart has to be moving the same acceleration, so the acceleration is the same. So in the second system, the acceleration is 1.31 meters per second squared. And here again you have the free body diagram, and essentially what they want to know now is what force is the professor exerting on the cart. And the force of the professor exerting on the cart minus the resistant force has got to equal the force net that results in the motion of the cart. Okay? And so what we have now is the 19 kilograms, which is exerted on by this net force and leads to the acceleration. So we have 19 kilograms times 1.31 meters per second squared, okay? And that has to be F net, and that has to equal F minus the professor. And this, so F professor, which is what we want, has got to equal this 19 times 1.31 plus the force of the opposing force, which is 24. And when you do the math here, you get 48.9 newtons. So that is the force that the professor is exerting to give the acceleration of the cart. So now let's look at a concept that I have alluded to previously, but now I'll explain in more detail in the context of Newton's third law, and that's the idea of a normal force. Now this is going to become even more important when we begin talking about friction in more detail. Here on the left in diagram A, we have a person holding a bag of dog chow, and the force of the hand on the bag holding it up is equal and opposite to the weight of the bag of dog chow. So F hand is equal to W. F hand is equal to W. Now the second diagram shows what happens when you put the chow on the table. Now most tables don't obviously sag like this, but indeed what has to happen is when you put the bag on the chow, the bag of chow on the table has to exert a force equal and opposite to the weight. And that perpendicular force equal and opposite of the weight is called the normal, or normal force, and is labeled almost always N, okay? So the weight of an object is the mass of the object times the force due to gravity, or the acceleration of gravity. The normal force is always perpendicular to the surface of the whatever the weight is being set on, and opposite to the weight of the object. So here's another problem that we're going to look at. We have a skier here, and the skier's mass is 60 kilograms, and the question is, what is the acceleration? First, if there is no friction, and second, if there's a friction of 45 newtons. So let's first look at it if there's no friction. Now, the important thing to understand is you have a weight which is always straight down, and that weight, because this individual is on an incline, can be divided into the perpendicular force, F perpendicular, and the parallel force, F parallel. Now F parallel is what causes the skier to go down the plane, and F perpendicular is what holds the skier on the plane, or on the inclined plane. And this, you see F parallel is the side opposite the angle, so it's going to be the total weight times the sine of 25 degrees, and this is going to be the weight times the cosine of 25 degrees. And the weight here is mass times acceleration, or 60 times 9.8 times the cosine of 25 degrees. I'm sorry, sine of 25 degrees. And this is going to be 60 times 9.8 times the cosine of 25 degrees. So the parallel force and the perpendicular force. And the parallel force, when you calculate it, is 248 newtons. And the perpendicular force is 533 newtons. This is what's responsible for the motion down the plane. So if we want to know how far we're accelerating, we go to F is equal to ma. So A is equal to F over m is equal to 248 divided by 60. And 248 divided by 60 is equal to 4.13 meters per second squared. So that's the acceleration down the plane. Now the only difference if you add friction is that you subtract the friction force from this value. So now F net is going to equal the parallel force minus the friction force, which is 248 minus 45, or 203. And then you do this again, except now you have 203 divided by 60, and that's going to equal 3.38 meters per second squared. So here you have a problem where you have the forces divided into their x and y components. This just shows what I just showed you, which is in any situation like this, you can always divide this into a parallel and a perpendicular component. The parallel component is always going to be the weight times the sine of the angle shown. The perpendicular component is always going to be the weight times the cosine of the angle shown. And look, notice that this angle is also equal to this angle over here. I'm having trouble with my computer here, sorry. This angle and this angle are always going to be equal. Before I go to the next part, let's take a look at this last slide. This is real important to understand before we go on to do some more problems. In this last slide, what we're looking at is tension, okay? You have what's known as a perfectly flexible connector. Obviously, no real connector is perfectly flexible, but the idea is there's no force required to bend it, okay? So it can bend without force being used. And this transmits tension, or T, and this is going to be parallel to the rope. Wherever the rope is, the tension is always parallel to that. The rope pulls in an equal and opposite direction to the weight. Notice that the tension here is equal and opposite to the weight down here. And when you hold it with your hand, this force, this tension experienced by the hand, is equal and opposite to this tension. The point being is the tension anywhere in a rope between the hand and the mass is equal. And once you've determined the tension in one location, then you determine the tension throughout all the locations between here, well, actually between here and here, this hook here, and that transmits all the way down to here. And this is the appropriate free body diagram here. So I'm going to stop this part at this point, and then when we come back in the next part, we'll start doing some problems working with tension.